All right, so the plan for today is to finish discussing the 3D coordinate system and vectors and start into the dot product and cross product. And then Monday, finish up anything we need to from today, finish up equations of lines and planes. And that should wrap up the course material. On Wednesday, the 8th, there is an optional review session from 1 to 3. So basically just treat that as office hours. We do have the Unit 3 exam this week, so make sure to complete that. And then the final exam is will be available Friday of this week, the 3rd through Friday the 10th. And it will be on WebAssign using Examity, same as the unit exams. Sample exams available. You may use a formula sheet, front and back of a standard size piece of paper. And like I mentioned a couple of times already, don't wait until the last minute to take the exam. I recommend taking it no later than Wednesday. That way, just if something pops up, there's some margin, you have some buffer to get anything worked out before Friday the 10th. And there are no due date extensions. I need to get, for all my courses, I need to get my final exams graded, final grades compiled, everything entered pretty much as quickly as possible so we can get a quick turnaround for folks who are planning their summer semester. Okay, are there any questions on anything? All right, our quotes of the day today, we have a couple quotes of the day for the last little bit here. Two of them are from the comedian Norm Macdonald, late comedian Norm Macdonald. The two are pretty similar to one another, but in the first one, he says, the idiot sees the world as good versus evil. The cynic sees the world as evil versus evil. The truth no one seems to be able to see is that the world is and always has been a battle of good versus good. And the second one, which he said, I think it was on one of the late shows a few years ago. It says here in this history book that luckily the good guys have won every time. What are the odds, right? The victors write the history, as they say. I think with all the craziness going on in the world today, it's maybe useful to just kind of keep that perspective that if we're tempted to see good versus evil and everything, then maybe we ought to just question the extent to which that is true. And then kind of the last quote, I guess, for the semester from my buddy Mark, and he's in St. Louis, works in finance. And he said one time, and I took note of it, I thought it was just a really good quote. 10 times out of 10, I take a questionable contract with a solid person over an ironclad contract with a questionable person. And of course, he was talking about finance stuff, but I think this applies to a lot of things in life, right? If you're looking for a contractor or something to do some work for you, the person means more than the paper. Or if you're, if you got a couple of job offers, you're trying to decide which one to take, maybe just looking at the one that has a little bit more salary or has a little nicer benefits or something, maybe only looking at that stuff might be a little bit short-sighted, instead looking at what's the culture of the organization, what's their longevity, things like that. Sometimes being with a more solid organization is better than a more flashy organization. Okay. So I want to quickly recap vectors, addition, scalar multiplication, and subtraction. So recall that two vectors are equal if they have the same magnitude and the same direction. We don't worry about whether they have the same location. So we can, in essence, move vectors around and they stay the same vector. So vector addition, let's suppose we have vectors like u and v. What does u plus v look like? Let me get myself a little more room here. So u plus v I take vector u, And vector u has an initial point and a terminal point, where the terminal point is the arrow. And then to the terminal point of u, I attach the initial point of v. And I see now I have a structure that has kind of an overall initial point and an overall terminal point. So that red vector is u plus v. Scalar multiplication, so multiplication by a number. If I have a vector u, then for instance, the vector 2u, or u plus u might look like that. Or the vector negative u, like that, or negative 5u would look like 5u, but then in the opposite direction. So that's how scalar multiplication works. If the number that we're multiplying by is positive, we change the magnitude to be the number we're multiplying by times the original magnitude, and we keep the direction the same. If it's negative, we multiply the magnitude by the absolute value of the scalar, and then switch the direction. We exchange the initial and terminal points. And then lastly, vector subtraction. So we think of u minus v as u plus negative v. Or if I have u and v, like up here, so there's u. And then if I have v, if this is v, then I note that negative v is the vector where I've swapped the initial and terminal points. So that's what negative v looks like. And well, before I do that, let me get this label out of the way. So u plus negative v, I put the terminal point of u and the initial point of negative v at the same location. And that gives me an overall vector u plus a negative v or u minus v. And we also noted that addition was commutative because we have this so-called parallelogram law. U plus v is the same as v plus u. So I think that's a pretty good, super quick recap of last time. And now we're going to move on to discussing components of vectors. So, I mean, it's all well and good to have this kind of geometric understanding of vectors, but a lot of times we want to impose this on a coordinate system. And we want to have a way of discussing components of vectors, or discussing vectors by their components. If we place the vector, let's call it u, where its initial point was at the origin, so either maybe 0, 0 in 2D or 0, 0, 0 in 3D will be the most common ones that we're going to work with, but this is a pretty general idea. It could be in other dimensions. But if our vector were positioned with its initial point at the origin, Then we consider the location of its terminal point in that coordinate system. Those coordinates are what we call the components of U. So if we had a two-dimensional system and we had some vector U that when we place its initial point at the origin, its terminal point ended up at 3, 4. So this is the point 3, 4. We could say that U equals 3, 4. We'll write vectors with angle brackets and try to restrict the use of parentheses to points. But often you'll actually just see the same notation for the coordinates of the vector in other contexts. But we're going to try to stick to vectors being represented by angle brackets and points being represented by parentheses, just to kind of keep things a little straight. Math already tends to kind of overuse some of our notation, particularly parentheses get used quite a bit. So having these angle brackets just, helps us to keep things straight a little bit what we're talking about. All right, so let's look at some properties. Let's suppose that the vector U has components A naught and B naught. Here we'll be in 2 dimensions, but all of this generalizes to 3 dimensions just fine. And V will have components alpha naught and beta naught. This way the A's and the alphas and B and beta we can keep them straight. I guess we don't need the knots right now. I'll actually get rid of the knots because I don't feel like writing them a bunch of times. We'll just make them A and B and alpha and beta. So then we could say the following, that the negative of a vector that negative just kind of distributes through. Negative U is negative A comma negative B. If we have a scalar multiple, C times U, that also distributes through. Each of the components just gets multiplied by C. The sum of 2 vectors, if I want to add 2 vectors together, it turns out I just add component-wise. Right, if I think of what my vectors are doing, U says kind of the first coordinate of U says maybe go to the right that distance, and the first coordinate of V says go to the right this other distance. And if I combine the 2 together, that's just going to the right the sum of those 2 distances. Or if one of those distances is negative, we interpret that as going to the left. And the same would be true for the second component. So if we want to add 2 vectors, we just add component-wise. Combining our summation formula here with the negative formula. If we want to subtract 2 vectors, we subtract component-wise. All stuff that we would really expect to be true, I think. Now we want to be a little careful. In another section or so, we're going to see that not every operation that we might think should be trivially easy like this is going to be trivially easy. So I mean, at this point, you're saying, well, yeah, of course this works, but it's not a given that this stuff works so nicely all the time. So for example, 2U plus 3V would be 2A plus 3 alpha and 2B plus 3 beta, for instance. we can see very clearly that the commutativity of vector addition holds by just the commutativity of scalar addition, right? We could swap the A and alpha and the B and beta, and then break that back apart, and we could see that we would get V bar plus U bar. So we can see from these components that vector addition has to be commutative. There's an identity element, an additive identity, the vector 0, 0. So the vector with 0 length. 0, 0 is often just denoted this way. The 0 vector is the additive identity. And so if we take a vector and add the 0 vector to it, we just get the original vector back. Right, because alpha and beta would both be 0 up here. So we just get vector AB again, or just U. We have scalar distributivity. So a scalar, a number, times the sum of two vectors, we can distribute. We get scalar times first vector plus scalar times second vector. And this just comes from basically combining those two properties. We also have a scalar associativity, which might, at first glance, it looks kind of obvious, but if you think about it, it's really saying something a little bit deeper than we might appreciate at first. On the left side here, we're saying I have two scalars, C and D, two numbers, C and D, and vector U. I'm saying if I multiply the two numbers together, get another number, and then multiply U by that number, that's the same result as actually taking one of the numbers, multiplying it by U, getting another vector, D U bar would be another vector, and then multiplying that new vector by C. So this might, this, at first glance, this seems obvious. At maybe a second glance, you say, oh, it's actually saying a little bit more. What's in parentheses over here is actually a vector, and what's in parentheses over here is actually a number. But then if we really think of this in terms of, say, our component example up here, well, then it makes a little more sense that we're just basically popping all of those constant multiples or those scalar multiples inside, and they're just hitting each term, each component of the vector. So I think it does make sense, but again, it says a little more maybe than at first glance it seems to say. Okay, so we have a definition, the magnitude of a vector. We've said that a vector has magnitude and direction, but we haven't really said what its magnitude is. We just said it's kind of the length of the vector when we draw it on the paper. But now that we have this idea of components, of something more of an algebraic structure attached to vectors, can we say what the magnitude of a vector is? Well, we talked about the distance formula in 2 and 3 dimensions. And we also said that the components of a vector are the coordinates of the point that the terminal point ends up with when we place the initial point at 0, 0. So the magnitude of the vector, also called the length of the vector, is just going to be the distance between 0, 0 and the coordinates that correspond to the components of our vector. So the length of the vector v1, v2, v3 would be what? v1 minus 0 all squared, or just v1 squared, plus v2 minus 0 all squared, or just v2 squared, plus v3 minus 0 squared, v3 squared, all under the square root. So we're just applying our same old distance formula to this new idea. And we call this, we write this in a notation that's similar to the absolute value notation. This is the magnitude of the vector v, or just the length of v, and we write it in a way that looks like absolute value of v. And there actually is kind of a deep connection between magnitudes and absolute values and so on. If we think of a number as just being kind of like in a sense, kind of a one-dimensional vector, it can have direction, positive or negative, and then its magnitude is the absolute value. Okay, a couple of notes. We say that a vector is a unit vector if it has length 1. So quite often we're interested in finding unit vectors. That's quite a helpful thing to be able to do. And by that, we mean it has length 1. And a second note is for any vector that's non-zero, that's not the zero vector, we can construct a unit vector in the same direction by taking that vector divided by its length. So if I have a vector v that's non-zero, I can construct a vector u as v over the length of v, or, well, when I say v over the length of v, what do I mean by that? I mean 1 over length of v. That's just a number. That's just a scalar multiplied by the vector v. Just to be clear exactly what I mean there. That's a vector that points in the direction of v, but has length 1. We have a super nice definition here for standard basis vectors. In 3D space, we have these what are called standard basis vectors. They get these kind of trademarked names, IJK, but let me zoom in a little bit here. They actually get these little hats over them. So I, J, and K have little hats over them. So it's like an I hat instead of like I bar. We don't really write it that way. This like I hat or J hat or K hat, those are like trademarked vectors. They mean specifically these 3 vectors. We call these the standard basis vectors. There's this idea in linear algebra of having a basis, having a way to represent points in a certain space. And these standard basis vectors are the unit vectors. Note that they all have length 1 that point in the directions of the positive x, y, and z axes. So I hat is the vector of length 1 that points in the direction of the positive x-axis, j hat for y-axis, k hat for z. So a question, if I have some random vector, u equals 10, comma, minus pi, comma, 1/2, can I write this in terms of the standard basis vectors? And if so, how would I do that? Well, I might start off by thinking, okay, what if I had I hat here? What if I had 1, 0, 0? Well, that's not quite u hat. The first component is 1, and I want my first component to be 10. How would I make my first component 10? Well, I suppose I could multiply by 10 in front, right? That would give me 10, 0, 0. I've used I hat times the coefficient to get my first component correct. But now my second component is 0, so what would I do next? If I do, say, plus a negative pi j hat, this would be minus pi times 0, 1, 0. So the 10 times 1, 0, 0 gives me first component 10, second component 10 times 0, 0, third component 0. But now for the minus pi times 0 gives me 0 added to the first component. But the minus pi hits against this 1 in the second component, gives me a minus pi in that second component. So now my second component matches what I want. And then I think we probably see the pattern, plus 1/2, plus 1/2 k. hat, or plus 1/2 times 0, 0, 1, which would put a 1/2 in the third component. So I see that I can break an arbitrary vector into its components like this. I can write an arbitrary vector in terms of coefficients times the standard basis vectors, and that's really the goal of finding a basis, is to be able to do this. So can this be generalized? Well, sure. If U was A, B, C, then U is just A, I hat plus B, J hat plus C, K hat. So super nice thing to remember. Sometimes it's nicer to write it this way. Sometimes it's nicer to write it that way, kind of depending on context, depending on what you're working on. But we can break the vector into its kind of component basis vectors, or we could leave it as a single vector. Okay, so any questions on vectors, either the kind of geometric side of things up here or the associated algebraic side of things? All right, so we've talked about addition and subtraction, scalar multiplication. They worked kind of the way that we would have hoped they would work. If we want to add two vectors, we just add their components. If we want to multiply by a scalar, we just multiply each component by the scalar. What if I want to multiply two vectors? What if I have U times, in some sense, V? I mean, I know if I say something like, 3 times 5, that means do like 5 plus 5 plus 5, do like 5 added to itself 3 times. Or if I have like 3U, that means kind of like add U to itself 3 times. So scalar multiplication means kind of repeat addition. But what is vector multiplication? If I multiply a vector V by a vector U, am I saying like add V to itself U bar times? Like, well, that doesn't really make much sense. So it's very important that U times V is typically not, let's say that this is A and B, and this is alpha and beta. It's typically not A times alpha, B times beta. This just doesn't make a lot of sense to do in any way that ties reasonably in with these kind of geometric structures up here. Now, kind of a little side note, maybe very much a side note, if you're working in a programming language, say something like MATLAB, and MATLAB it's kind of a mathematical programming language. It's geared towards being able to do things like linear algebra and things like that pretty nicely and easily and quickly and efficiently. So it's not, as nice as say something like Python or C for doing like general kind of computing stuff for, graphics or whatever. But for doing math stuff, MATLAB is pretty nice. It works with matrices and vectors and things like that very nicely. So if you tell it, I want to multiply two vectors together, it's going to want to do that in a certain way, but it's not going to be this way. But sometimes you just want to treat two lists of numbers as just lists and then multiply them together, outside of the context of what we're talking about here with vectors and so on. So you actually have to kind of tell MATLAB, you have to use a slightly different operator to tell MATLAB, like, no, I don't want you to multiply these like vectors. I want you to multiply them this way. So there are some cases where you might have some lists of numbers that you want to multiply this way in some context, even maybe in a mathematical context. So it's not to say that this kind of idea is always absurd, but the thing is that in the context of vectors that we're talking about here, where we're talking about three-dimensional space and three-dimensional coordinate system and a thing that has magnitude and direction and so on, that's where it doesn't make really so much sense to define multiplication this way. So how do we define multiplication then? Well, the answer is that we have two ways of defining multiplication. 12.3 represents one of those ways, the dot product, and 12.4 the other way, the cross product. And we're going to go through these next couple of sections. And then maybe after we finish these two sections, we'll zoom out a little bit and we'll say, okay, what are these two ideas of multiplication really kind of qualitatively doing, right? We'll go through the details and we'll see how these work and so on. We'll look at some properties and so on, go through some examples, but then we'll zoom out and we'll say, okay, like, what are these two ideas of multiplication actually doing, and why are there two of them and not five or not seven or not one? So let's look first at the dot product. Suppose we have two vectors in three-dimensional space. Here, u is u1, u2, u3, and v is v1, v2, v3. Then we define the dot product of u and v to be, we do kind of do this multiplying component-wise kind of idea. However, importantly, we add the results together. So vector u dot vector v, the dot product of u and v, turns out to be a scalar, right? We multiply the first two components together. That gives us a number. We do the same to the second and the third, gives us three numbers, and then we add those three numbers together. We don't just put those three numbers into another vector, but we add those three numbers together. That gives us a single number, a real number that's a scalar. Sometimes the dot product is even called the scalar product of the two vectors. And then as a nod to something that's a little more general in linear algebra, that this is a special case of, sometimes the dot product is even called the inner product of two vectors, u and v. The idea of an inner product is more general than just the dot product, but this would be the special case of an inner product. And sometimes, like I said, it's called the scalar product because it results in a scalar in a number. When it's in the context of an inner product, sometimes you will see this notation used. And you might recognize this notation from some other fields. Pops up in physics sometimes, that kind of thing. So this kind of a notation often denotes the inner product. Okay, so what are some properties of the dot product? Well, if I dot product a vector by itself, so u dot u, this would give me u1 times u1, or u1 squared, plus u2 squared plus u3 squared. That's very similar to the magnitude or the length formula. It's just the square of the length. So if I dot a vector with itself, I get the length squared. The dot product does distribute over addition. So u dotted with v plus w gives me u dot v plus u dot w. Pretty easy to check just by using our definition up here. U dotted with the zero vector, right? u1, u2, u3 dotted with 0, 0, 0, of course, gives us the scalar 0, the real number 0. The dot product is commutative, easily seen by the commutativity of just scalar multiplication. We can swap all the u's and v's and then break it back apart, and we would get v dot u. And we have associativity this way as well. Before, with scalar times vector, we saw that scalar times vector, that was associative. Here we have scalar times vector in a sense, where by vector times vector, I mean dot product. So here I could take scalar times the first vector, get a new vector from that, and then dot it with the second vector. Or I could dot the two vectors together first, and then multiply the resulting number by the scalar c. In either case, I get the same thing. Right. This cu gives me a vector back, which I then dot against another vector to get a number. U dot v gives me a number, which I then multiply by c to get another number. And whichever way that I do it, I get the same number at the end. We have a super nice little theorem here. If theta is the angle between two vectors, u and v, so if I placed, so say this is u and this is v, what I mean the angle between them is if I place their initial points at the same point, then there's an angle between those two vectors. If theta is that angle, then u dot v is length of u times length of v times the cosine of the angle between them. Now, in this form, this maybe isn't all that practically useful, because I can find the dot product so easily up here. Why would I do all of this down here? But where it's practically useful is that if I'm interested in knowing the angle between two vectors, the dot product's easy to find, their lengths are easy to find. I can figure out the length, I can figure out the angle between the two vectors given their lengths and their dot product. So if I need to find an angle between the vectors, this would be a good formula to use. And a corollary to that, two vectors u and v are orthogonal, they meet at right angles if and only if u dot v equals 0. So of course, u dot v equals length u, length v, cos theta. And if this is 0, let's suppose that u is not equal to the 0 vector and v is not equal to the 0 vector. Maybe I should say two non-zero vectors. Then what does that mean? Well, length u and length v will both be positive numbers then. So this says cos theta equals 0. And when is cosine of theta 0? That's when theta is 90 degrees. Or I guess we could say like 270 degrees, but that's just 90 degrees in the other direction. So if we always take the angle between two vectors, if we always consider that that means the angle less than 180 degrees, it would be kind of silly to say the angle between the two vectors was this angle here. Then we see that the dot product is 0 if and only if the two vectors are orthogonal. Right. If they're orthogonal, cos of 90 is 0, and the dot product is 0. And if the dot product is 0, then the cosine is 0, which means that theta is 90 degrees, they're orthogonal. Okay, let's look at the cross product. So we'll get to see the two types of products. And that probably will take us about to the end of class today. And then when we come back again, we'll look at some examples. We'll look at some examples and we will talk about qualitatively what does the dot and cross product mean. Okay, so the definition of the cross product. So again, if we have U and V, we can define the cross product of U and V by the following thing. U cross V, so we use kind of an X looking times here, where for the dot product, we used kind of a bullet in between the two. U cross V is a vector. So it's a vector that has three components. It has a first component that's U2V3 minus U3V2. It has a second component and a third component. So it's a vector in what we would call R3. So we're going this might seem like a very strange way to set up a product. Like, why would we do all of this? We're going to have a method that maybe helps us to maybe generate this formula. So you could write this formula down and just have it on your formula sheet if you just wanted to use it like this. We're going to look at a way to remember the formula in a minute here. Something to note, though, is that it turns out that U cross V, this vector here, this is a vector that is orthogonal to both U and V. Or in other words, if I consider the vector U cross V, and I dot that with U, that gives me 0. Or if I consider U cross V, and I dot that with V, that also gives me 0. So if I have in, say, 3-dimensional space, vectors U and V, and if I have a vector that is orthogonal to both of them, that meets both of them at 90 degrees, that could be a vector like this, or it could be a vector like this. There's a little bit of ambiguity here. It could be a given vector or its opposite. They both would be orthogonal to both of the original vectors. So which one do we choose? Well, if I have U cross V, where U is first, V is second, we use something called the right-hand rule to decide which direction the vector is going. So I think of taking my right hand. If you look at your two hands facing away from you and you see which one your thumb and first finger makes an L, that's your left hand, use the other hand. And if I curl my fingers from U to V, so in this case, if I kept my hand with my thumb facing up and curled around, I would curl from V to U. So it's got to be the other way. My thumb has to be facing down. Then when I curl my fingers around, they'll curl from U to V with my thumb facing down. So what the right-hand rule says is take your right hand, curl your fingers from U to V, or from the first vector to the second vector, whatever they may be, in this case, from U to V. and then look at the direction your thumb is pointing. In this case, my thumb would be pointing down. My thumb will be pointing in the green direction. Now you might think to yourself, well, wait, that means if I did V cross U, well, V cross U, my fingers would go to V, then to U, my thumb would be pointing up instead of down. Right, U cross V points down, and V cross U is its opposite, it points up. In this case, our multiplication, this cross product, is not commutative. U cross V is negative V cross U. They're not exactly the same. Okay, so I want to make a note on, you can either view it as kind of where this formula comes from, or you can view it as just a kind of helpful memory device for that formula. So let's consider U cross V. Well, the first thing that I want to do is I want to talk about this idea of determinants and a related idea of cofactor expansion. We're going to use these ideas to help us remember this formula up here, or just in general to help us compute cross products. So we have this idea of a determinant, and this particularly applies to a matrix. Matrices are intricately linked to vectors. So a matrix is a two-dimensional array of numbers. So we might have, say, A1, A2, B1, B2 in a matrix like this. And often matrices are denoted as matrices by square brackets that surround them like that. Sometimes they're also denoted by parentheses that surround them in the same way. I can compute the determinant of a matrix. So this is a matrix. It's what we would call a 2x2 matrix, 2 rows and 2 columns. The determinant of a matrix we denote the same way with this 2x2 grid, but we use basically like absolute value signs around the whole thing. Instead of square brackets or instead of parentheses, we use vertical bars. And I see that I have a top left and a bottom right component of my matrix. I multiply those together. So on that main diagonal going top left to bottom right, multiply those numbers together. I have an off diagonal going from bottom left to top right. And I subtract them this way. So I have A1, B2 minus A2, B1. And we call this the determinant of that matrix. We're not going to talk much about why this is an interesting number or why we would be interested in computing this. But just a little side note, what a matrix does when you apply a matrix to a vector, it can do two things. It can rotate that vector, and it can change its magnitude. It can rotate it and stretch it. The determinant tells me how much I stretch the vector whenever I apply this matrix to the vector. So I stretch the vector's length by this number here whenever I apply this matrix to a vector. That's a linear algebra concept. We're not going much more deeply into that than what I've just said, but just in case you're interested, that's kind of what it means. Okay, so this is for a 2x2 matrix, kind of a two-dimensional structure. What about for a 3x3 matrix? I could have a 3x3 matrix like this, A1, A2, A3, B1, B2, B3, C1, C2, C3, and I could take its determinant. Right. This is a 3x3 matrix or a three-dimensional structure. So how can I take this determinant? There are kind of two ways. There's the kind of formal way, the cofactor expansion way, and then there's a little trick. So we'll do the cofactor expansion way, we'll look at that, and then we'll look at the trick and see if that can be helpful. Okay, if I want this determinant, what will I do? I'll first choose a pivot as one of the entries in the top row. So I'll start with A1, and then I'll multiply by, I noticed that if I like cross out the row and column that A1 is in, then I'm left with kind of what looks like a 2x2 matrix, B2, B3, C2, C3. So I have A1 times, and then this B2, B3, C2, C3 matrix, I'll take its determinant. Then I'm going to choose the pivot to be the second entry in the top row, A2. I have to switch the sign here, but I switch the sign, I have A2, so I have negative A2. Again, I get rid of the row and column that that one is in. And then I see I'm left with four numbers that, again, kind of look like a 2x2 matrix, B1, B3, C1, C3. And then I do the same thing basically one more time. I switch my sign again, plus A3, I eliminate that row and column from consideration. And I'm left with something like a 2x2 matrix, B1, B2, C1, C2. I take its determinant. And now I can expand all of these out. I have A1 times this 2x2 determinant, just like up here, is B2, C3 minus B3, C2 minus A2 times B1, B1, C3 minus B3, C1, and then plus A3, B1, C2 minus B2, C1. And at this point, I just have a big, long calculation to get some number, right? This is how I calculate a 3x3 determinant or a higher level determinant. If I had a 4x4, I would use this to get four 3x3 determinants. And then from each of those, I would get three 2x2 determinants. And you can tell that this is somewhat of a cumbersome thing to do by hand. So what is U cross V then? It is the determinant if I put I, J, and K in the first row. if I basically treat those kind of as if they were scalars and just put them in that first row. And then U comes first, so I do U1, U2, U3, use 3 components. And then V comes next, V1, V2, V3. We see all these minus signs floating around here, right? We can see how now when we switch U and V, if that changes what rows they're in, that changes what side of the minus sign things are on. That's what makes that kind of anti-commutativity happen. But what can I see? I can see that I get I, which would be A1, times what? B2C3 or U2V3 minus U3V2. I get minus J. I'm just matching up these 2 bits, these 2 lines, right, with that matrix. So minus J, which would be where A2 was, times what? B1C3, but that's U1V3, minus U3V1, and then plus K times U1 V2 minus U2 V1. And that should be, fingers crossed, what we have up here, right? For our first component, U2 V3 minus U3 V2. And that's what we see here, for instance. There is a little trick we can do to make finding 3x3 determinants even a little easier. If I have my determinant like this, I can append 2 columns to the end. I can just copy my first 2 columns over. And then what I can do is go top left to bottom right, like this, and like this. And these all come in positively. So this should be I times U2V3 plus J times U3V1 plus K times U1V2. And then I take my opposite diagonals, the ones going like this. There's 1, there's 2, there's 3. These come in with a minus. I'll put this down a little bit. So I get minus K hat times V1 U2 minus, oops, the next one is minus I hat V2 U3. And then the next one is minus J hat V3 U1. So I have I hat times U2 V3 minus U3 V2, for instance. And the others should work out as well. So this idea for computing 3x3 determinants is kind of the shortcut. You copy your first 2 columns over, and your kind of 3 main diagonals going top left to bottom right. You multiply those with a plus, and then the off diagonals with a minus. So that can be a little bit quicker, a little bit of a shortcut method. Okay, so that finishes our time for today, but when we come back, we'll talk about some properties and things with the cross product. And then we'll kind of zoom out a little bit and say, really, what are the cross product and dot product doing? I mean, it seems, the dot product maybe seems like kind of a reasonable thing to do. The cross product seems very silly. But what are they really doing? And we'll see that there's actually a good reason that they're set up the way that they are set up.